Thanks, Dieter, for the introduction, and also hello from my side. My name is Markus Ehrly. I am team leader for concept simulation at FEV in Aachen, and I want to give a presentation about alternative propulsion system. My colleague before explained how to maintain and to monitor complex systems, and that should be the motivation of us to not hesitate to use complex systems in the future. On the left side, we can see some information from the news that some requirements for the maritime business is changing in future. So we can see that more and more regions think about applying zero emission zones where ships are not allowed to make any emission at all. And furthermore, the news are telling that the world's marine business is responsible for a certain share of the CO2 emissions, and so also for the global warming. And all of this gives new requirements, and this we can see here on the right side, and they are the power supply with internal combustion engine off to come into a zero emission zone and to also have low NVH. The future powertrains need to reduce the pollutant emissions in a wide operation area. We need highly efficient power supply for low fuel consumption and on the other side, low CO2 and operation costs. And nevertheless, we want to have improved performance, especially in the transient operation, and we need to ensure a safe and reliable operation. So now on the left side, we can see what are the challenges of such a hybrid application. And these are very clear. The system complexity is increased against a normal system. And this will increase and strongly increased development effort and an increased requirement to the system robustness. We will end up with higher system costs and most probably increased weight and volume. And we have the challenge that some components availability is not as good as for conventional components. Nevertheless, on the right side, you can see some information from the typical propulsion system manufacturers, and what we can see, all of them are working on hybrid systems. They have already detect the benefits, and they develop such system in parallel to the conventional. Then on this slide, I want to give you the definition of an hybrid powertrain for the marine business in the view of FEV. And for us, a hybrid system is that beside the fuel tank, at least one more energy storage is available that could be charged or discharged by one or more onboard energy converter during the operation of the ship. And this we can see on the left side. So we have in red an additional energy storage that could be charged via an energy converter out of the fuel tank, or it can provide the energy again via an energy converter to supply mechanical energy, electricity, or heat, or it can directly provide it. Furthermore, it is possible that this additional energy storage is recharged in the Haber for using green electricity coming from the infrastructure of the Haber. How to characterize such a hybrid system, and one way to do this is shown here. We see on the y-axis the add-on power of a hybrid system, so how much add-on power the system can provide, independently of the engine power, and on the x-axis the duration, how long this add-on power can be supplied. And this results at the end in different size of the energy storage, which is shown with the number of the battery symbols. And at the end, the hybrid system is strongly defined by the size of the energy storage and of the battery system. To give some examples, we see on the upper right corner in system with a high add-on power and with a long duration, and this could be used for cruise ships in zero emission zones, for example, when they need to provide a full hotel load for a certain time to be operated in the zero emission zone. As the next example, we have a high duration of the hybrid power, but a small add-on hybrid power. And an example for this would be a cargo ship or a yacht application, which is driving with low speed in the harbor in the zero emission zone, or provides on a low level a hotel load without driving in zero emission zone. The last example we can see on this slide, a system with a high add-on power of the hybrid system, but at the same time, it's only possible to provide this for a quite short time. And this application could be used for an acceleration of a sport boat application, or to cover high load peaks in the hotel load for a cruise ship or other application with a high unstable hotel load. Coming to different setups of a hybrid system, we can see on the left side that we change now from a very easy setup with a combustion engine and a propeller on the crankshaft to a hybrid system which can be a parallel system where we have an additional e-motor on the shaft of the combustion engine, or in serious application where we have an electric motor driving a propeller and an engine which is an internal combustion engine which is driving a generator. So when we look to the right side, we have applied also in gearbox on the top, and on the right lower side, we have applied gearboxes and clutches. And what we can see out of this, that the system complexity increases strongly, even if we have only one engine who drives the system. From one, we come up to several possible solutions. So the system complexity is increasing. On the next slide, we see this for a two combustion engine setup. And we have to say two combustion engine is still low looking to ship applications. But here we combine now different scenarios, and we can see on the very left in combination of one parallel hybrid engine with a conventional engine. Then we see two parallel hybrid engines. Then we see a conventional engine and a hybrid and a serial hybrid engine. And on the right side, we see a combination of a parallel application and a serial application. And this is only a few possible combinations for two engines. There are even more available, and this shows us clearly that there is a high number of different variants possible, and is much higher than what we can have in the automotive industry, which is mainly because in the automotive industry we have only one combustion engine and not several of them. Then we come to the hybrid strategies. And here the main hybrid strategy or idea is to mask operation areas of the combustion engine that are not beneficial. What we can see now in the beginning, we see the masking of unbeneficial low load operation. And the easiest way to do this is shown in the diagram. Is we come from a low load operation with high specific fuel consumption, we go to a high load or a higher load operation with a better fuel consumption by recharging the battery. If the battery is full, then we can switch off the engine and supply the ship with power from the battery and decharge the battery. If the battery is empty, then we start from the beginning and recharge in a higher load point. And with this strategy, we can reduce the emissions and the fuel consumption. Next strategy is if we have two engine or more engine in place, then they are running both on low load. We can decide to go with one engine to a higher load point and switch the other engine off and have so an overall benefit in fuel consumption and in the most cases also for the pollutant emission. Beside the low load operation, we can also mask high load operation, and the biggest driver here is to mask transient operation where the engine is speeding up, has in the most cases too less air and also an inefficient combustion, and this operation areas are masked out by a load shift down. So the hybrid system provides additional load and gives the engine time to come to the target power. And this gives a strong benefit in pollutant emission and also a smaller benefit in the CO2 emission, and is a method for engines or power systems with a high dynamic operation profile. And as a last one, we can also mask unbeneficial high load operation by applying a load shift down, at least for some time till the battery is empty or on a low level. Then for sure, we cannot go on with this strategy and we have to go to the high load operation back. Beside the operation strategy, we can go one step further and we can design a dedicated hybrid engine to generate even better fuel consumption potential. How we are doing this? We are now saying that the load request of the engine, in the most cases the transient capabilities, can be reduced because we have an add-on system from the electric machine, and we can have now an engine with a very small operation area and in high efficiency inside this operation area, and ensure the requirements of the power supply system by the hybrid system. This is mainly done by reducing of specific torque and power for better efficiency, then reducing the engine map area, reducing of dynamic load build-up capabilities, and to make a right sizing of the combustion engine to have at the end the best fuel consumption benefit. Typical method to do this is customer or making or designing, optimizing the boosting system and the friction layout and the combustion system in the most times to a smaller operation area and so with a higher efficiency. On this slide, we have made a summary of benefits for different marine applications from yacht and cargo ship and cruise ship and working ship like a tugboat. And we have done this for several categories. And what we can see in total is that we have much more pluses than minus. So we see for the most ships is a hybrid system beneficial. And what we can see clearly that it's most beneficial for a yacht application and a working ship, and it is limited for a cargo ship. And what is beneficial and what not depends strongly on the layout of the hybrid system and also on the operation profile of the ship. Is the ship always running on full load, the hybrid system cannot do much. And this is clear. And beside of the benefits, we also have to say if an operation with zero emissions is required, we have no other chance than to go to a hybrid system. If there are further benefits or not, there is no other way. And then we have also performed in small calculation for an sport boat or yacht application. And what we can see is we come on from the left side from a conventional system with two main engines with 1 megawatt each and a small generator to provide the electricity with 60 kilowatt and no battery. We go to a hybrid layout with two parallel hybrid main engine. The combustion engine has still 1 megawatt power, and in addition, a 100 kilowatt e-motor. So we have a hybridization of 10%, which is quite low. And we have still the genset with 60 kilowatt for hotel load, more or less as a backup. We installed additionally a battery of 250 kilowatt hour. This allows us an e-drive of 1 hour with 10% of the combustion engine load, and furthermore, an additional hour of operation load, of hotel operation. For the operation strategy, we run below 10% power request emission-free by switching off all engines, and we recharge the battery during the in operation time when the main engines are on higher load than 10%. This we have done for 3 operation scenarios because they are very important for the hybrid system layout. First scenario is a scenario with a high e-drive share. So we have a high share of power below 10%. This we can see with the black bars. So we are running the most time below 10% or at 70% and only a small share on 100%. The second scenario is a scenario which is not beneficial for a hybrid system. It's a scenario where we run limited below 10% and a high share of 80% at 90% power. So on a quite high level. So it's a ship which is more or less driving and has small hotel load, and it's always driving on full speed. And as a third scenario, we have a scenario with a high share of low load operation and only limited at higher load. The genset load is for all 3 scenarios the same. Overall, it's around 50% of the load with the highest share at 30% of the power. Then we can see on the next slide the results of these small investigations. And we can see for the first scenario, which is the scenario with the high e-drive share, that we can reduce the fuel consumption by 1.5% only by applying the hybrid system and using the operation strategy. Then if we change the engine size, so we are not making a dedicated hybrid engine, we are just changing the engine size, and we are going to a 10% bigger main engine, we change the operation profiles, and we can then get a benefit of 3.2%. For scenario 2, the potential is lower, but this was clear from the beginning because of the high share of high load. And here we can get with the hybrid system a benefit of around 0.7%. And then if we install again a 10% bigger main engine, we can come to a benefit of 2.2%. If we come to the scenario 3 with a high share of low load operation, we can see that the hybrid system gives us a benefit of around 2%. And if we have a dedicated engine, we saw first of all that a bigger engine is giving no benefits at all. But if we go for a smaller engine, we can, for this scenario, reach a benefit of 2.6%. It's clear because then the engine is running a lot of time in low load operation, and there the smaller engine gives a benefit. So what can be seen out of this easy investigation is that the operation profile of a ship and the layout of the hybrid system is very important at development phase. And then we come to to the next thing is what are the challenges for a hybrid system layout. And there are a wide range of load profiles and boundary conditions that could be appear. Then we have low production number per layout. We have to find the optimal hybrid system setup out of plenty of possible concepts. And we have to optimize the hybrid operation strategy. So what are the FAV solutions? Is a requirement setting process to clearly define what are the operation conditions or what are the most likely operation conditions of the clients, and to make all the boundaries clear at the beginning. Then a highly flexible system simulation approach with a comprehensive component library, fast simulation executions, allowing us a high number of simulations, automatic system setup for a high number of variants that could be investigated, flexible controls, and simulation of several operation profiles. The optimization of the hybrid strategy and the setup and the hardware layout is done in one loop, and the development of smart operation strategies already in the concept phase. And here is a short extraction of our hybrid system concept development process. So at the beginning, as already said, we have to fix the boundary conditions and the requirements and to set up the simulation model. And here more or less some questions that need to be answered at the beginning to bring the complete process in the right direction. Then if the basics are done, we come to the system optimization. And here at the beginning, the definition of possible system and the property ranges is set. Then a DOE model is used to optimize the hardware parameter, the operation parameter, and this is done for several most likely operation scenarios and profiles. And within this DOE approach, a lot of simulations are done. We are speaking here of up to 1,000 simulations per operation system or possible system that are performed to find the optimum. And at the end, when all the systems, the simulations are done and optimization is done, and in final assessment, and which gives the best system for the given boundary conditions, and also already the fuel consumption and the emissions of the chosen system. And then I want to make a summary of my presentation. First of all, the maritime hybrid power supply system can improve the pollutant emissions and the fuel consumption, and there are not so much technologies available that can reduce the fuel consumption and the pollutant emissions with one technology. The hybrid application have an energy storage that could be charged and discharged during operation. Then upcoming zero emission zones and new CO2 regulations are a strong motivation for hybrid systems. Fuel consumption reduction could be achieved but strongly depends on hybrid system layout and operation profile. The drawbacks are a high system complexity leads to a high development effort. And the solution for this is a simulation-based concept development process that ensures a high product quality and the cost and time efficient development. Then I thank you for your attention.